Hello everyone. In this particular lecture, we'll have a look at how much data needs to be generated or in an RNA-seq experiment. RNA-seq experiment, the first RNA sequencing that we saw earlier was mRNA-seq. As you all know, mRNA sequencing, out of the entire genome, your mRNA covers 2% of your genome, 2% of the genome. If you consider the genome to be 3 into 10 to the power of 9 bases, and 2% of this would make up to 6 into 10 to the power of 7 bases. This means to cover your entire mRNA in the genome, you need to sequence 6 into 10 to the power of 7 bases once. The thumb rule here is that for an RNA-seq experiment, for each sample, you will have to have a coverage of around 50x. Now, what does this mean? Means that if you have your genome like this, and you have your genes A, B, and C, this is A, B, and C, it means that every nucleotide of this particular gene has to be sequenced at least 50 times. Now, if it is 6 into 10 to the power of 7 base pairs to cover the entire mRNA once, for covering it for 50 times, you'll have to multiply it with 50. This makes a total of around 3 into 10 to the power of 9 bases. This again accounts to 3 GB of data per sample we are talking about. Again, the same question here. The vendor would ask you that you need to convert the data into millions of reads. Now, how do you convert this data into millions of reads? As I earlier told you, each read, in this case of mRNA sequencing, as I told you, is 75 base pairs. That's what I told you. So each read is around 75 base pairs. And in a file, you'll be having several reads of 75 base pairs. Now you'll have to count how many of these reads would cover your 3 GB of data. So what do? You take 3 into 10 to the power of 9 base pairs and then divide it by 75 to get the number of reads. This is 3 into 25. And this is now 100 into 10 to the power of 7 by 1. So this, by 25. So this makes it 4. So this is around 40 into 10 to the power of 6. So this will give you 40 million reads. So this will give you a 40 million reads. So this is how you calculate from GBs of data to want a coverage of around 50 times, right? You get to have around 40 million reads. And this 3 GB is converted into millions of reads. And the base pair length here is around 75 base pairs. And the same fundamental holds good. If it is 2 into 75 here, as we have discussed in one of our lectures, it means that one file will be having the forward reads of around 20 million and the reverse reads of around 20 million. So the total will account to around 40 million reads. So that's how you calculate your quantum of data that is needed for your mRNA-seq experiment. Now we'll extend this RNA-seq for the whole transcriptome. RNA-seq for the whole transcriptome. Now, when you talk about the whole transcriptome would include what? As I explained, this whole transcriptome includes your LNC RNA, your mRNA, and your circular RNA. Now, out of the entire genome, it is considered that your LNC RNA is around 3% and your mRNA is around 2%. A word of caution here, the percentages that I am considering here are from the literature that I have taken currently, but you have so many papers mentioning about different percentages for LNC, mRNA, and circular RNA. Now, for example, in one of the papers, it has mentioned that mRNA can vary from 1.2% to 1.5%. Here, the purpose of this lecture is to just tell you how to calculate the quantum of reads for the percentage of your interest. So the percentage that needs to be considered depends on the researcher who's going to perform the experiment. Now, if we have a look at all this in total, you have around 8% of your entire genome covers your LNC, mRNA, and cRNA, that is circular RNA. Now, if you have 3 into 10 to the power of 9 as your total genome length, and 8% of this, it makes out the total whole transcriptome, this accounts to now, let's say, we'll just do this. This is around 24 into 10 to the power of 7. Right? Now, if you have generated 24 into 10 to the power of 7 bases, the thumb rule again is to cover this entire transcriptome, which covers LNC, mRNA, and circular RNA 50 times, like what I have explained. This will now make around 24 into 10 to the power of 7 into 50. And if you multiply this, you will get around 1200 into 10 to the power of 7. And this will make up to 12 GB of data. And if we are converting this 12 GB again into millions of reads, and what was the size of reads I told you that you need to generate for the whole transcriptome? I told you the size of the reads is 2 into 150. So what do we do? 150 base pair. So what do we do now? We simply take 12 GB of data, 12 into 10 to the power of 9, and divide it by 150. This makes it around 8. This makes it around 3/4, and this is 5. And now you are going to have around how much? Let us say it is 40 into 10 to the power of 7 by 5. This will make around 8 into 10 to the power of 7, which is nothing but 80 into 10 to the power of 6, which makes around 80 million reads. 80 million reads. And again, if you're talking about paid end reads, there'll be 40 million forward and 40 million reverse. 40 million reads. So this is what is the quantum of data that you need to generate for your whole transcriptome.